Hello everybody, this is Gordon. We're back in physics for another set of problems on motion in a vertical plane. We have, as before, our relationships for falling bodies, relationships between velocity and time, height and time, which can be solved for time as an expression of height and velocity as an expression of height, and then for projectiles, equations for range and time of flight. The first problem, the Empire State Building, 1,472 feet high. How long would it take for an object dropped from the top to reach the ground? And what would its final velocity be? We have height given again as 1,472 feet. We're looking for time and velocity. We can use the equation for time as the square root of 2 times the height divided by the gravitational constant, which we'll use as 32 feet per second squared, given height is provided to us in feet. And when we do the arithmetic, we have time is equal to 9.6 seconds. And then given that we have seconds now, we can use velocity is equal to gravitational constant times time. So we'll have 32 feet per second squared times 9.6 seconds to find the value for the velocity of 307 feet per second. And that's the first problem. The second problem, a ball is thrown horizontally with a velocity of 12 meters per second. We're asked how far has the ball fallen in 1 second and in 2 seconds. The thing here to realize is that horizontal motion and vertical motion are independent of each other. The fact that the ball is thrown horizontally 12 meters per second has nothing to do with how far it's fallen in the perpendicular direction in 1 second and 2 seconds. So we'll use the equation height is equal to 1/2 times the gravitational constant times time squared. So for height, or the distance fallen in 1 second, it's 1/2 times 9.8 meters per second squared, that should be, times 1 second squared to get 4.9 meters. And the height, or the distance fallen in 2 seconds, 1/2 times 9.8 meters per second squared times 2 seconds squared, and come up with a distance fallen of 19.6 meters. The third problem, a water rocket is launched at an angle of 40 degrees above the horizontal with a speed of 300 meters per second. We're asked to find its range and time of flight. We have theta as 40 degrees and v sub 0, the initial velocity, as 300 meters per second. We're asked to find range and time. We use the projectile equations. And so we'll have range equal to v sub 0 squared, 300 meters per second, quantity squared divided by the gravitational constant 9.8 meters per second squared, that should be again, times the sine of 2 times theta, theta being 40, we'll have the sine of 80 degrees. And when we do the arithmetic, the range turns out to be 9,044 meters. The time, 2 times the initial velocity divided by the gravitational constant times the sine of theta. So 2 times 300 meters per second divided by 9.8 meters per second squared times the sine of 40. And again, when we do the arithmetic, we come up with a value for time as 39 seconds. The fourth problem, a body in free fall reaches the ground in 5 seconds. We're asked from what height is it dropped and what was its final velocity. So we're given t is equal to 5 seconds. We're asked to find v, the final velocity, and h, the height from which it was dropped. And so again, we can use the equation for height is equal to 1/2 times the gravitational constant times time squared. So 1/2 times 9.8 meters per second times 5 seconds squared to come up with a value for the height of 122.5. That should be meters. Thank you very much. And then a value for the velocity, 9.8 meters per second squared times 5 seconds. Final velocity is 49 meters per second. Last question, a good question. If the initial velocity of a projectile is doubled, what is the effect on the maximum range? Basically, we're asked if v2 is equal to 2 times v1, what difference does it make? Well, we have range 1 as v1 squared divided by the gravitational constant times sine of 2 theta. Range 2 is equal to velocity 2 squared times g, or divided by the gravitational constant times 2 theta. But v2 is equal to 2v1, so we can substitute that in and have 2v1 squared divided by the gravitational constant times sine 2 theta, which is equal to 4v1 squared divided by g sine 2 theta, and that is equal to 4 times r1, or r with the range with the first velocity. And so it turns out then that if you double the initial velocity of the projectile, the range is 4 times greater. And that's the end of the set. Thanks for watching.